Everything you see in space tells a lie. Stars, galaxies, planets, they're all cosmic decorations hiding the real story. Right now, invisible forces control your entire existence. You can't see them. You can't touch them. Yet they shape every corner of the universe. Tonight we're discovering what actually runs the cosmos. The glowing stuff in telescopes represents less than 5% of reality. Before we dive into this invisible empire, drop a comment about what you think space is mostly made of. If you enjoy these cosmic revelations, consider subscribing. Scientists tried to weigh galaxies in the 1970s. The math didn't work. A brilliant astronomer named Vera Rubin studied how stars moved around galaxy centers. She measured their speeds with incredible precision. What she found seemed to break every rule of physics. Stars at galaxy edges raced around way too fast. Think of planets in our solar system. The farther out they are, the slower they orbit. But galaxy stars didn't follow this pattern at all. The visible matter couldn't create enough gravitational pull. Not even close. Those outer stars should have been flung into deep space billions of years ago. Yet there they were, holding stable orbits. Something massive and completely invisible was keeping them in place. Everything you consider normal barely registers in cosmic accounting. Your body, every star, every planet. It's all statistical noise. Scientists have now measured the universe's complete inventory. They used multiple methods to double-check their shocking results. The numbers remain consistent and disturbing. Ordinary matter makes up less than 5% of everything that exists. That's every atom, every element, every piece of matter you've ever seen or touched. We're the cosmic minority. The rest operates under completely different rules. It shapes reality while remaining utterly invisible to human senses. Scientists discovered matter that breaks the normal rules. This stuff has mass and creates gravity, but produces no light whatsoever. They call it dark matter because it doesn't interact with electromagnetic radiation. No photons, no heat signatures, no radio waves. It's gravitationally present but electromagnetically absent. This invisible matter doesn't behave like regular atoms. It can't form stars or planets. It doesn't clump into solid objects, yet it outweighs all visible matter by a ratio of more than 5-to-1. Dark matter creates the scaffolding that holds the universe together. Without it, galaxies would simply dissolve into scattered stars. The term dark matter describes our ignorance more than the substance itself. Scientists chose this name because the material remains completely undetectable to light-based observations. This naming reflects humanity's limitation, not the matter's properties. We call it dark because our eyes and instruments can't register its presence. The matter itself might be perfectly normal by cosmic standards. The label stuck because it captures the fundamental mystery. Here's matter that clearly exists but refuses to reveal itself through any known electromagnetic process. We're essentially blind to the majority of cosmic matter. It's like trying to understand a symphony while being able to hear only 5% of the instruments. Scientists discovered something even stranger than invisible matter. They found a mysterious energy that actively pushes space itself apart. This force works opposite to gravity. Instead of pulling things together, it creates repulsion on cosmic scales. The expansion of the universe isn't slowing down, it's speeding up. They named this phenomenon dark energy because it remains as mysterious as dark matter. This energy fills every cubic inch of space, creating a constant outward pressure. Dark energy comprises roughly 68% of the universe's total energy budget. It's the dominant force shaping cosmic evolution across billions of light years. Modern astronomy has completed the universe's first accurate census. The results humble every assumption about cosmic importance. Dark energy dominates with 68% of the universal budget. Dark matter accounts for 27% of everything that exists. Together, these invisible components control 95% of reality. Ordinary matter, stars, planets, gas clouds, and people, represents less than 5% of the cosmic total. We exist in a universe where almost everything operates beyond human perception. This census reveals humanity's true cosmic status. We're not just small in space and time. We're made of cosmic minority matter in a universe dominated by invisible forces. Scientists face an unprecedented challenge. How do you study matter that refuses to interact with light or electromagnetic radiation? Direct detection remains nearly impossible with current technology. Dark matter particles might pass through your body right now without leaving any trace. They interact so weakly with ordinary matter that trillions could flow through Earth every second. Gravity provides the only reliable signature of dark matter's presence. Scientists must infer its existence from gravitational effects on visible matter. It's like studying an invisible person by watching how objects move around them. This limitation forces astronomy into indirect detective work. The majority of the universe remains accessible only through gravitational fingerprints. The discovery of dark matter and dark energy exposed fundamental gaps in human knowledge. Our best theories can't explain 95% of the universe. The standard model of particle physics describes visible matter beautifully. It predicts the behavior of atoms, molecules, and chemical reactions with incredible precision, but it completely fails to account for cosmic reality. Einstein's relativity equations require additional terms to match observations. Scientists must add placeholder components, dark matter and dark energy, to make the math work. This represents the greatest crisis in modern physics. Our theories work perfectly for the visible 5%, but offer no explanation for the invisible 95%. The glowing universe that fills astronomy textbooks represents mere decoration on a cosmic stage. Everything visible serves as window dressing for invisible architecture. Stars, galaxies, and nebula create beautiful images but play supporting roles in cosmic evolution. The real action happens in dark matter networks that span billions of light years. Visible matter follows paths carved by invisible scaffolding. Galaxy formation, star birth, and planetary systems all depend on dark matter's gravitational guidance. We see the results but miss the cause. The cosmos operates like an iceberg. The beautiful visible portion above water hides the massive invisible foundation below. Dark matter and dark energy represent astronomy's most profound puzzle. Despite decades of research, scientists understand almost nothing about these dominant cosmic components. Multiple Nobel Prizes await whoever solves these mysteries. Thousands of scientists worldwide dedicate their careers to detecting dark matter particles or understanding dark energy's nature. The mystery deepens with every new observation. Advanced telescopes reveal more evidence for invisible matter while providing no clues about its fundamental nature. Dark energy remains even more enigmatic. Humanity has discovered that 95% of reality operates beyond our current comprehension. We're cosmic archaeologists trying to understand a civilization while seeing only 5% of the evidence. The discovery of dark matter and dark energy represents the greatest revolution in human cosmic perspective since Copernicus displaced Earth from the universe's center. This revolution strikes deeper than previous paradigm shifts. Copernicus moved humanity from the cosmic center, but we remained made of normal matter in a comprehensible universe. Now we discover that even matter itself exists as a cosmic minority. The implications challenge every assumption about reality's nature. If 95% of the universe operates beyond human detection, what else might we be missing about the fundamental structure of existence? We stand at the beginning of a new chapter in cosmic understanding. The visible universe that inspired centuries of wonder represents just the opening page of a far more mysterious story. What happens when you try to weigh a galaxy cluster and the numbers don't add up? Fritz Zwicky faced exactly this problem in 1933. Zwicky studied the Coma cluster. That's a massive collection of galaxies bound together by gravity. He measured how fast individual galaxies moved within this cosmic neighborhood. The galaxies raced around far too quickly. They moved like cars speeding around a racetrack with no barriers to keep them on course. According to basic physics, they should have been flung out into space long ago. Zwicky calculated the cluster's total mass based on visible light from stars. The results shocked him. The visible matter couldn't generate enough gravitational pull to hold those speeding galaxies in place. He concluded that invisible matter must be hiding throughout the cluster. Zwicky called it dark matter, matter that exists but produces no detectable light. Every planet in our solar system follows a simple rule. The farther from the Sun, the slower it orbits. Mercury races around quickly while distant Neptune crawls along its orbital path. Astronomers expected galaxy stars to behave the same way. Stars near the galactic center should orbit rapidly. Stars at the galaxy's edge should move much more slowly. But galaxy rotation curves tell a completely different story. These graphs show how stellar speeds change with distance from the galactic center. The results break every expectation. Stars maintain roughly constant speeds regardless of their distance from the galaxy's center. It's like discovering that all planets in our solar system orbit the Sun at identical velocities. This impossible behavior demands an explanation. Invisible matter must be distributed throughout each galaxy to create these uniform orbital speeds. Could one woman's observations revolutionize our understanding of cosmic reality? Vera Rubin answered that question definitively in the 1970s. Rubin studied the Andromeda galaxy with unprecedented precision. She measured the orbital velocities of stars at different distances from the galactic center. Her equipment could detect tiny shifts in starlight caused by stellar motion. The data revealed an impossible pattern. Stars at Andromeda's outer edges moved just as fast as stars near the center. This violated every principle of orbital mechanics. Rubin's measurements were so precise they couldn't be dismissed as observational error. She had documented a fundamental contradiction between theory and reality. Her work provided ironclad proof that galaxies contain far more matter than meets the eye. The invisible component outweighs visible stars by a ratio of at least 6-to-1. How much mass does it take to hold a galaxy together? Scientists thought they knew the answer until observations proved them spectacularly wrong. Astronomers added up all the visible matter in typical galaxies. They counted stars, gas clouds, and cosmic dust. They calculated the total gravitational force this matter could generate. The results created an impossible deficit. Visible matter could account for only 10 to 15% of the gravitational force needed to prevent galactic dissolution. The remaining 85 to 90% remained completely unaccounted for. This wasn't a small calculation error. Scientists were missing the majority of cosmic matter. Their most basic assumptions about the universe had crumbled. The missing mass problem forced astronomy to confront an uncomfortable truth. Humans could see only a tiny fraction of cosmic reality. When two massive galaxy clusters collide, what happens to their different types of matter? The bullet cluster collision provided a natural laboratory to answer this question. During the collision, ordinary matter behaved differently than dark matter. Hot gas from both clusters slammed into each other and slowed down dramatically. Think of two water balloons colliding and splashing everywhere. But dark matter passed right through the collision zone. It doesn't interact with ordinary matter except through gravity. The dark matter from both clusters continued moving at high speed. This cosmic crash physically separated dark matter from ordinary matter across space. Astronomers could map where each type of matter ended up after the collision. Gravitational lensing revealed the dark matter's location by showing how it bent light from background galaxies. The evidence confirmed dark matter's existence beyond any reasonable doubt. Can something bend light while remaining completely invisible to human detection? Einstein's general relativity predicted this possibility decades before astronomers observed it. Massive objects warp the fabric of space and time around them. Light traveling through warped space follows curved paths instead of straight lines. This effect is called gravitational lensing. Astronomers discovered that light from distant galaxies gets distorted while traveling toward Earth. The distortion patterns reveal invisible mass between us and those distant light sources. This invisible mass creates gravitational lenses without producing any detectable electromagnetic radiation. It has mass but generates no light, heat, or radio signals of its own. Gravitational lensing provides a direct method to map dark matter's distribution throughout the universe. We can see dark matter's gravitational fingerprints even when the matter itself remains invisible. What would the universe look like if dark matter didn't exist? Computer simulations provide a definitive answer to this fundamental question. Scientists programmed detailed simulations of cosmic evolution starting from the Big Bang. They ran identical scenarios with and without dark matter to compare the results. Simulations without dark matter failed to reproduce the universe we actually observe. Galaxies couldn't form properly. Large-scale structures never developed. The cosmic web of galaxies and galaxy clusters simply didn't emerge. Only simulations including dark matter successfully recreated realistic cosmic architecture. Dark matter provides the gravitational scaffolding that allows ordinary matter to clump into galaxies and stars. These computational experiments prove dark matter's essential role in cosmic evolution. Without it, the universe would remain a featureless soup of dispersed gas. The largest structures in the universe follow invisible blueprints drawn by dark matter. Galaxies aren't randomly scattered through space. They follow specific patterns. Astronomers have mapped the three-dimensional distribution of galaxies across billions of light years. These maps reveal a cosmic web of filaments connecting dense galaxy clusters. The visible galaxies trace the outline of underlying dark matter structures. Think of Christmas lights strung along an invisible framework. You can see the lights but not the wire supporting them. This cosmic web stretches across the entire observable universe. Dark matter forms the skeleton while galaxies provide decoration along its major highways. The web structure matches computer simulations of dark matter evolution with remarkable precision. Invisible matter shapes the architecture of everything we can see. how do you detect something that refuses to interact with light or electromagnetic radiation? Modern astronomy developed entirely new observational techniques to tackle this challenge. Advanced CCD cameras revolutionized astronomical imaging in the 1980s. These electronic detectors could measure stellar positions and brightnesses with unprecedented precision. Sophisticated spectrographs allowed astronomers to measure tiny Doppler shifts in starlight. These instruments could detect stellar motions accurate to a few kilometers per second. Computer-controlled telescopes enabled long-term surveys of thousands of galaxies. Automated systems could measure rotation curves and velocity dispersions on industrial scales. These technological advances transformed dark matter from theoretical speculation into observational reality. Better tools revealed the invisible universe hiding in plain sight. Scientific revolutions require overwhelming evidence to overturn established theories. The case for dark matter eventually became impossible to ignore. Multiple independent observation methods all pointed to the same conclusion. Galaxy rotation curves, gravitational lensing, galaxy cluster dynamics, and computer simulations all demanded invisible matter. The evidence accumulated from different types of cosmic objects across various distance scales. Dark matter's influence appeared in individual galaxies, galaxy clusters, and large-scale cosmic structures. No alternative theory could explain the full range of observations without invoking some form of invisible matter. The evidence forced even skeptical scientists to accept dark matter's existence. By the 1990s, dark matter had transformed from controversial hypothesis to established fact. The invisible universe had finally revealed itself to human science. Dark matter particles behave like cosmic ghosts. They pass right through each other without any interaction whatsoever. This property sets them apart from every type of normal matter humans have ever encountered. Regular matter collides constantly. Gas molecules bump into each other billions of times per second. Solid objects resist penetration. Even the thinnest materials eventually stop projectiles with enough collisions. But dark matter operates under completely different rules. Dark matter particles can occupy the same space simultaneously without affecting each other's motion. They experience no friction, no collisions, no resistance. This collision-free behavior explains why dark matter can form such large, stable structures throughout the universe. Without collisions to slow them down, dark matter particles maintain their cosmic dance for billions of years. Gravity represents dark matter's only connection to the normal universe. This invisible substance responds to gravitational attraction but ignores every other fundamental force of nature. Dark matter doesn't interact with electromagnetic radiation. No photons, no radio waves, no heat signatures. It remains completely transparent to light while still possessing mass and creating gravitational effects. The weak nuclear force and strong nuclear force also have no effect on dark matter particles. These forces govern atomic structure and radioactive decay in normal matter, but dark matter operates independently. This selective interaction with gravity alone makes dark matter incredibly difficult to detect directly. Scientists must rely on its gravitational fingerprints to study this elusive cosmic component. Every galaxy sits inside a massive sphere of dark matter called a halo. These invisible structures extend far beyond the visible edges of galactic disks, creating cosmic architecture on enormous scales. Galaxy halos contain roughly 85% of each galaxy's total mass. The visible stars, gas, and dust that create beautiful astronomical photographs represent only the decorative elements within this invisible framework. Dark matter halos follow a specific distribution pattern. They're densest at the center and gradually become thinner toward the outer edges. Think of a cosmic onion with invisible layers extending outward. These halo structures formed before visible galaxies existed. Dark matter created the gravitational wells that later captured ordinary matter and allowed star formation to begin. Galaxies grew inside pre-existing dark matter scaffolding. Dark matter earned its classification as cold because of how slowly its particles moved during the universe's early epochs. This seemingly simple property determined the entire structure of cosmic evolution. Cold dark matter particles moved at relatively low speeds when the universe was young. Fast-moving particles would have prevented the formation of small-scale structures like galaxies and solar systems. If dark matter had been hot instead, meaning fast-moving, it would have smoothed out cosmic irregularities. The universe would have remained a featureless expanse without galaxies, stars, or planets. The cold nature of dark matter allowed gravitational clumping to occur on multiple size scales. This enabled the hierarchical structure formation that created everything from galaxy clusters to individual stellar systems. Dark matter density decreases in a predictable pattern from galaxy centers toward their outer edges. This distribution follows precise mathematical relationships that scientists can measure and model with remarkable accuracy. The density profile starts extremely high at galactic centers. Moving outward, the density drops according to specific power laws that remain consistent across different galaxy types and sizes. Astronomers have measured these density profiles in hundreds of galaxies. The pattern remains remarkably uniform regardless of galaxy mass, age, or morphological type. This consistent distribution pattern provides crucial evidence for dark matter's gravitational nature. The mathematical precision of these profiles matches theoretical predictions for collision-free gravitational systems. Dark matter creates invisible gravitational wells throughout the universe. These cosmic depressions in space-time act like collection basins for ordinary matter, enabling galaxy and star formation. Without dark matter's gravitational influence, ordinary matter would have remained dispersed as thin gas throughout cosmic space. The universe would contain no concentrated structures capable of igniting nuclear fusion. Dark matter wells provided the initial gravitational seed points where normal matter could begin accumulating. As ordinary matter fell into these invisible traps, it gained enough density to form the first stars. This process continues today as dark matter halos guide the ongoing formation of cosmic structures. Every galaxy exists because dark matter first created the gravitational architecture necessary for its birth. Dark matter particles within galaxy halos move in completely random directions. This chaotic motion creates a dynamic equilibrium that has maintained galactic stability for billions of years. Unlike the organized orbital motion of stars and planets, dark matter particles follow no predictable paths. They move like molecules in a gas with velocities pointing in every possible direction. This random motion prevents dark matter from collapsing into compact objects. The particles' kinetic energy balances against gravitational attraction, creating stable, extended halos around galaxies. Scientists measure this velocity dispersion to determine total halo masses. The faster dark matter particles move within a halo, the more massive that halo must be to contain their motion gravitationally. When galaxy clusters collide, dark matter and ordinary matter behave in fundamentally different ways. These cosmic crashes provide natural experiments that expose dark matter's unique properties. During cluster collisions, ordinary matter experiences drag and friction. Hot gas clouds slam into each other and slow down dramatically, like cars crashing in slow motion. Dark matter passes through collision zones without any deceleration. Its collision-free nature allows dark matter halos to continue moving at high speed, while ordinary matter gets left behind. These separation events prove that dark matter truly exists as a distinct substance rather than a modification of gravitational laws. The different behaviors during collisions provide definitive evidence for dark matter's particle nature. Dark matter forms a nested hierarchy of structures that spans the entire observable universe. Large dark matter halos contain smaller subhalos, which contain even smaller substructures in an intricate cosmic pattern. This hierarchical organization matches computer simulations of dark matter evolution with stunning precision. The predicted structure formation process appears to match reality exactly. Subhalos represent the remnants of smaller dark matter concentrations that got absorbed by larger structures over cosmic time. They continue to orbit within their parent halos like cosmic fossils. Astronomers can detect these substructures through their gravitational effects on nearby stars and gas clouds. The subhalo population provides detailed tests of dark matter theories and computer models. Dark matter particles interact with each other so weakly that scientists can place strict limits on their interaction strength. These constraints help narrow down the possible nature of dark matter particles. If dark matter particles interacted more strongly with each other, they would have created observable effects in galaxy centers. Dense dark matter regions would have developed different density profiles than what astronomers actually measure. The weakness of dark matter self-interactions allows particles to pass through each other almost like they don't exist. This property maintains the smooth, extended halos observed around galaxies. These interaction limits rule out many theoretical particle candidates for dark matter. Only particles with extremely weak self-interactions can match the observed properties of cosmic dark matter halos. Dark matter remains cold throughout cosmic history. Unlike ordinary matter, which can heat up through collisions and electromagnetic interactions, dark matter maintains its low temperature indefinitely. Normal matter reaches thermal equilibrium by exchanging energy through collisions and radiation. Hot regions cool down while cold regions warm up until everything reaches the same temperature. Dark matter lacks these energy exchange mechanisms. Without collisions or electromagnetic interactions, dark matter particles cannot reach thermal equilibrium with their surroundings. This permanent coldness preserves the small-scale structure of dark matter halos. If dark matter could heat up, it would expand and erase the detailed structure that enables galaxy formation and cosmic evolution. Dark matter particles have remained stable for the entire about 14 billion years of the universe's history. This remarkable longevity exceeds the lifetime of most other cosmic phenomena. Many subatomic particles decay into lighter particles within microseconds or milliseconds of their creation. Even protons might eventually decay after unimaginably long timescales. But dark matter shows no signs of instability or decay. Astronomical observations confirm that dark matter halos formed early in cosmic history still exist today with their structures intact. This stability requirement severely constrains theories about dark matter's fundamental nature. Only particles with lifetimes longer than the age of the universe can serve as viable dark matter candidates. Astronomers in the 1990s studied exploding stars called supernovae. These cosmic explosions serve as cosmic lighthouses, because they can be standardized to a known brightness. Scientists use them to measure distances across the universe. But something was wrong with the distant supernovae. They appeared significantly dimmer than calculations predicted. At first, astronomers suspected observational errors or cosmic dust blocking the light. Multiple research teams confirmed the same puzzling results. Distant supernovae consistently appeared fainter than they should based on their known brightness. The observations were too consistent to dismiss. The dimness meant these exploding stars were farther away than expected. If the universe had been expanding at a constant rate, the distances should have matched predictions perfectly. Instead, the universe had been expanding faster in recent cosmic time. Something was accelerating cosmic expansion against the pull of gravity. Every object with mass in the universe should slow down cosmic expansion through gravitational attraction. The combined gravity of all stars, planets, and dark matter should gradually decelerate the universe's growth. For decades, astronomers debated whether the universe would expand forever or eventually collapse back on itself. Both scenarios assumed that gravity would slow the expansion over time. Reality proved both assumptions wrong. Precision measurements revealed that cosmic expansion has been speeding up for the past about 5 billion years. The universe grows faster today than it did in the past. This acceleration violates every intuitive understanding of how gravity works. Instead of everything pulling together, something pushes cosmic space apart with increasing strength. The discovery forced scientists to accept an uncomfortable truth. An unknown energy dominates cosmic evolution and overpowers the gravitational attraction of all visible matter. Gravity always attracts. Every piece of matter in the universe pulls on every other piece of matter. This attractive force has shaped cosmic evolution since the Big Bang. But the accelerating expansion reveals a repulsive force operating on cosmic scales. This mysterious energy pushes space itself apart rather than pulling matter together. Unlike gravity, which weakens with distance, this repulsive effect grows stronger as space expands. The more space exists, the more pushing force gets generated across cosmic distances. This anti-gravitational behavior creates a cosmic tug-of-war. Gravity tries to pull matter together while dark energy pushes space apart. On the largest scales, dark energy wins decisively. The repulsive nature of this force explains why cosmic acceleration has been increasing over time. As the universe expands, more space gets created, generating even more repulsive energy. Einstein originally included an extra term in his equations of general relativity. He called it the cosmological constant and designed it to prevent the universe from collapsing under its own gravity. When astronomers later discovered cosmic expansion, Einstein regretted adding the cosmological constant. He famously called it his greatest blunder because it seemed unnecessary. The discovery of accelerating expansion rehabilitated Einstein's discarded term. The cosmological constant provides a mathematical way to describe the repulsive energy driving cosmic acceleration. This constant represents energy that exists everywhere in space with exactly the same density. It doesn't dilute as the universe expands because space itself contains this mysterious energy. Einstein's blunder turned out to be one of his most prescient insights. The cosmological constant now serves as the leading mathematical description of dark energy. Quantum mechanics predicts that even completely empty space contains energy. This vacuum energy emerges from fundamental uncertainty principles that govern subatomic reality. According to quantum theory, particle pairs constantly pop into existence and disappear throughout empty space. These virtual particles exist for incredibly brief moments before annihilating each other. The energy of these quantum fluctuations might provide the driving force behind cosmic acceleration. If vacuum energy has repulsive properties, it could explain dark energy's behavior. However, theoretical calculations of vacuum energy produce values that are completely wrong. The predicted energy density exceeds observations by more than 100 orders of magnitude. This mismatch represents the worst prediction in the history of physics. Either quantum mechanics fails on cosmic scales, or vacuum energy isn't the source of dark energy. Most forms of energy become diluted as the universe expands. Matter spreads out over larger volumes, reducing its density over time. Radiation also becomes stretched and weakened by cosmic expansion. Dark energy behaves completely differently. Its density remains perfectly constant even as space grows. When the universe doubles in size, dark energy density stays exactly the same. This constant density means that dark energy's total amount increases as the universe expands. More space creates more dark energy without any known source or mechanism. The universe contained equal amounts of matter and dark energy about 5 billion years ago. Since then, dark energy has grown to dominate the cosmic energy budget. Today, dark energy outweighs all matter by more than 2 to 1. This dominance will only increase as cosmic expansion continues into the future. Ordinary matter creates positive pressure that resists compression. When you squeeze a gas, it pushes back against the compression force. This positive pressure always opposes the applied force. Dark energy creates negative pressure instead. This strange property means dark energy acts like a cosmic spring that pushes outward in all directions simultaneously. Negative pressure provides the mechanism for gravitational repulsion in Einstein's equations, while positive pressure enhances gravitational attraction. Negative pressure creates gravitational repulsion. The strength of dark energy's negative pressure exactly equals its energy density. This specific relationship produces the maximum possible repulsive effect allowed by general relativity. This negative pressure explains why dark energy accelerates cosmic expansion rather than just maintaining a constant expansion rate. Dark energy became the dominant component of the universe relatively recently in cosmic history. For most of the universe's existence, matter controlled cosmic evolution through its gravitational effects. The transition occurred when the universe was about 9 billion years old. Before this point, matter density exceeded dark energy density and cosmic expansion was decelerating. After the transition, dark energy density surpassed matter density and cosmic acceleration began. This marked a fundamental shift in how the universe evolves over time. The takeover happened because matter density decreases as the universe expands while dark energy density remains constant. Eventually, the constant energy overtook the declining matter density. This cosmic regime change determines the universe's ultimate fate. Dark energy now controls cosmic evolution and will likely continue to do so forever. Scientists characterize dark energy using an equation of state that relates its pressure to its energy density. This equation determines how dark energy affects cosmic expansion. The equation of state parameter for dark energy equals -1. This specific value produces the observed acceleration of cosmic expansion with maximum efficiency. Different values would create different cosmic behaviors. Values greater than -1 would produce less acceleration. Values less than -1 would cause even more dramatic expansion effects. The measured value remains remarkably close to exactly -1 across cosmic time. This precision suggests that dark energy represents a fundamental property of space itself. The equation of state provides a crucial test for different theories of dark energy. Future observations will determine whether this parameter truly equals -1 or varies slightly over time. Multiple completely different observation techniques have confirmed the reality of cosmic acceleration. This convergence of evidence from various sources strengthens confidence in the discovery. Supernova observations provided the first clear evidence for acceleration. Measurements of the cosmic microwave background radiation independently confirmed the same conclusion through entirely different physics. Studies of large-scale cosmic structure evolution also support accelerating expansion. The growth rate of galaxy clusters matches predictions for a universe dominated by dark energy. Observations of distant galaxies using different redshift measurement techniques yield consistent results. All methods point to the same cosmic acceleration timeline. The agreement between independent observation methods rules out systematic errors or alternative explanations. Cosmic acceleration appears to be a genuine feature of universal evolution. If cosmic acceleration continues indefinitely, the universe faces a cold and lonely future. Dark energy will eventually separate galaxies so far that they disappear beyond each other's horizons. One possibility is the Big Rip scenario. If dark energy strengthens over time, it will eventually overcome all other forces and tear apart every structure in the universe. Another possibility is heat death through maximum entropy. The universe will expand and cool until all energy sources are exhausted and no more work can be performed. Both scenarios result in a universe where no complex structures can exist. Stars will burn out, black holes will evaporate, and even atoms might eventually decay. The ultimate cosmic fate depends on dark energy's precise properties and whether they remain constant over time. Current observations suggest a cold, empty universe awaits in the distant future. Dark energy's density appears to have remained the same throughout cosmic history, while galaxies form and stars burn out. This mysterious energy seems to maintain a constant strength across time. Scientists have measured dark energy's behavior from when the universe was much younger. They studied distant galaxies and cosmic structures from different epochs. The energy density shows no clear variation within measurement limits. This constancy defies normal experience with energy sources. Stars burn their fuel and fade away. Radioactive elements decay over time. Even the cosmic microwave background radiation weakens as space expands. But dark energy operates under completely different rules. It doesn't seem to decay, weaken, or change properties over billions of years of cosmic evolution. This time-invariant behavior suggests dark energy may represent a fundamental property of space itself, rather than a temporary cosmic phenomenon. Every cubic meter of space appears to contain the same amount of dark energy. This uniformity extends across the observable universe without any clear detectable variations. Astronomers have searched for regions where dark energy might be stronger or weaker. They've examined galaxy clusters, cosmic voids, and dense stellar neighborhoods. The energy density appears identical everywhere within current measurements. This homogeneity contrasts sharply with matter distribution throughout the cosmos. Matter clumps into galaxies, stars, and planets while leaving vast empty regions between structures. Dark energy shows no clear preference for crowded or empty regions of space. It fills every location with the same energy density regardless of local cosmic conditions. This smoothness implies that dark energy doesn't seem to interact with matter or respond to gravitational fields in any measurable way. Normal energy becomes weaker as the universe expands. Matter spreads out over larger volumes, reducing its density. Radiation gets stretched to longer wavelengths, losing energy in the process. Dark energy breaks this fundamental rule completely. As cosmic space doubles in size, dark energy density stays the same. The energy doesn't thin out or weaken despite enormous expansion. This behavior means the universe's total dark energy content continuously increases. More space creates more dark energy without any known source or mechanism providing the additional energy. The apparent violation of energy conservation on cosmic scales represents one of physics' deepest mysteries. Dark energy seems to emerge from nowhere as space expands. This non-diluting property explains why dark energy has become the dominant component of the modern universe despite being weaker than matter in the past. Dark energy doesn't seem to interact with any form of matter through any known physical mechanism. It operates in isolation from stars, planets, gas clouds, and even dark matter particles. Unlike gravity, which couples to mass, or electromagnetic forces, which affect charged particles, dark energy remains indifferent to material presence. It neither attracts nor repels any form of matter. This interaction-free behavior allows dark energy to coexist with matter without creating obvious effects on small scales. Solar system dynamics remain essentially unaffected by dark energy's presence. The lack of interaction helps explain why dark energy remained undetected for so long. Its effects only become apparent on cosmic scales where vast distances amplify the cumulative influence. This isolation from matter makes dark energy extremely difficult to study through direct laboratory experiments or local astronomical observations. Dark energy affects the universe through its influence on space-time geometry. Unlike matter, which curves space through its mass, dark energy creates curvature through negative pressure alone. Einstein's equations describe how energy and matter curve the fabric of space and time. Dark energy produces a specific type of curvature that causes space itself to expand at an accelerating rate. This geometrical effect operates independently of matter content or distribution. Dark energy curves space uniformly regardless of whether galaxies or empty voids occupy specific regions. The curvature created by dark energy has the opposite sign from matter-induced curvature. While matter causes space to contract gravitationally, dark energy causes space to expand repulsively. This purely geometrical nature distinguishes dark energy from other cosmic components that interact through particle exchanges or field interactions. Dark energy appears to provide the right amount of repulsive force to keep the universe close to geometrically flat. This balance helps determine the overall shape of cosmic space-time. The universe's total energy density hovers near the critical value that produces flat geometry. Too little energy would create curved space that eventually collapses. Too much would create space that expands too rapidly for structure formation. Dark energy's contribution to this critical density has grown over time as matter density decreased through cosmic expansion. The energy stepped in to maintain flatness just as matter could no longer provide enough density. This remarkable fine-tuning suggests either incredible cosmic coincidence or deeper physical principles governing universal evolution that scientists don't yet understand. The maintenance of flat geometry allows the universe to support complex structures like galaxies and solar systems across cosmic time. Dark energy's repulsive effects prevent new large-scale cosmic structures from forming in the modern universe. Galaxy clusters can no longer grow by capturing additional galaxies from surrounding regions. Before dark energy dominated, gravity could pull matter together across vast distances to build increasingly massive structures. Galaxy clusters continued growing by accreting smaller groups and individual galaxies. But accelerating expansion now stretches space faster than gravity can pull distant matter together. The cosmic web of filaments and clusters has essentially frozen in its current configuration. Future cosmic evolution will see existing structures gradually separate rather than merge into larger systems. The era of hierarchical structure growth has ended permanently. This cessation of structure formation marks a fundamental transition in cosmic evolution driven entirely by dark energy's anti-gravitational effects. Dark energy shrinks the size of our observable universe by accelerating cosmic expansion beyond the speed of light at sufficient distances. This creates an event horizon beyond which we can never receive information. In a decelerating universe, light from any distant galaxy would eventually reach Earth given enough time. Cosmic expansion would slow the light but never prevent its arrival completely. Accelerating expansion changes this completely. Galaxies beyond a certain distance recede faster than light can travel toward us. Their light will never reach Earth regardless of how long we wait. This cosmic event horizon currently lies about 16 billion light-years away. Galaxies beyond this distance remain forever beyond human observation despite existing in our universe. The shrinking horizon means the observable universe becomes more limited over time, rather than growing larger as intuition might suggest. Dark energy behaves like a perfect fluid with properties that seem impossible according to normal physics. Its pressure equals -1 times its energy density, creating maximum repulsive effects. Normal fluids have positive pressure that resist compression. When you squeeze water or air, it pushes back against the applied force. The pressure always opposes external compression. Dark energy's negative pressure creates the opposite effect. It acts like a cosmic spring that pushes outward in all directions simultaneously without any external force driving the expansion. This negative pressure violates everyday intuition about how fluids behave. The pressure doesn't result from particle collisions or thermal motion like normal fluids. The specific ratio of pressure to energy density produces exactly the right amount of gravitational repulsion to accelerate cosmic expansion as observed. Dark energy cannot be detected through direct measurement techniques available to modern science. Its effects only become apparent through careful analysis of cosmic-scale observations spanning billions of years. Laboratory experiments cannot isolate or concentrate dark energy for study. The energy density remains far too low to create measurable effects on human scales, despite dominating cosmic evolution. Even astronomical observations must rely on indirect signatures of dark energy's influence on cosmic expansion and structure formation. No telescope can image dark energy directly. Scientists must infer dark energy's properties from statistical analysis of thousands of distant galaxies and cosmic structures. The evidence emerges only through precise measurements of cosmic distances and expansion rates. This detection challenge means our understanding of dark energy remains limited despite its dominant role in cosmic evolution. The universe's most important component remains deeply mysterious to human science. Massive objects bend light rays as they travel through space. This effect, called gravitational lensing, works like a cosmic magnifying glass that reveals hidden mass throughout the universe. Einstein predicted this light-bending phenomenon decades before astronomers could observe it. His theory of general relativity showed that mass warps space-time itself, forcing light to follow curved paths. When light from distant galaxies passes near invisible dark matter clumps, the light gets deflected from its straight-line path. The deflection creates distorted images of background galaxies that astronomers can measure precisely. By analyzing thousands of distorted galaxy images, scientists can map where dark matter concentrations exist. The technique works because dark matter's gravitational effects bend light even though the matter itself produces no light. Gravitational lensing provides the only direct method to see dark matter's distribution across cosmic space without relying on its effects on visible matter. Weak gravitational lensing creates tiny distortions in galaxy shapes that are almost impossible to detect individually. But statistical analysis of millions of galaxies reveals the invisible cosmic web. Individual galaxy distortions are incredibly small. They change a galaxy's apparent shape by only 1 to 2%. No human eye could detect such subtle alterations in astronomical images. However, computers can measure these tiny shape changes with extraordinary precision. When astronomers analyze the shapes of millions of distant galaxies simultaneously, clear patterns emerge. The statistical analysis reveals how dark matter clumps and filaments stretch across billions of light years. Each galaxy acts like a tiny probe sampling the gravitational field created by invisible matter. This weak lensing technique has mapped the largest structures in the universe by detecting gravitational effects too subtle for any single observation to reveal. Astronomers measure how fast stars orbit around galaxy centers using the Doppler effect. This technique reveals when galaxies contain far more mass than their visible stars can account for. The Doppler effect shifts starlight to different colors depending on stellar motion. Stars moving toward Earth appear slightly bluer, while stars moving away appear slightly redder. Precise measurements of these color shifts allow astronomers to calculate exact orbital velocities for stars at different distances from galactic centers. The resulting graphs are called rotation curves. These rotation curves consistently show that stars orbit too rapidly for the visible matter present. The orbital speeds indicate total galaxy masses that exceed visible mass by factors of 5 to 10. The speed measurements provide ironclad evidence that invisible dark matter dominates galaxy masses while contributing nothing to their brightness. X-ray telescopes detect hot gas trapped within galaxy clusters. The gas temperature reveals the total gravitational field strength, allowing scientists to weigh entire clusters including their invisible components. Galaxy clusters contain vast clouds of gas heated to temperatures exceeding 100 million degrees Celsius. This superheated gas emits powerful X-ray radiation that space-based telescopes can detect and map. The gas temperature directly reflects the cluster's total gravitational pull. Stronger gravity heats the gas to higher temperatures by converting gravitational potential energy into thermal energy. By measuring gas temperatures throughout galaxy clusters, astronomers can calculate total cluster masses. The results consistently show that visible matter accounts for only 10 to 15% of cluster masses. X-ray observations provide independent confirmation that dark matter dominates large cosmic structures while remaining completely invisible to optical telescopes. Scientists use supercomputers to model how dark matter should evolve throughout cosmic history. These simulations predict observable consequences that astronomers can test against real observations. The simulations start with the known properties of dark matter immediately after the Big Bang. Computers then calculate how gravity would cause this matter to clump over billions of years. These computational models predict exactly how dark matter should distribute itself into halos, filaments, and cosmic voids. They also predict how ordinary matter should respond to dark matter's gravitational influence. Comparing simulation results with actual astronomical observations allows scientists to test whether their understanding of dark matter matches reality. The agreement has been remarkably precise across multiple observation types. Computer modeling provides the theoretical framework that connects dark matter's invisible presence with its observable gravitational effects on visible cosmic structures. Type Ia supernovae serve as cosmic lighthouses because they always produce the same total amount of light. Astronomers use these exploding stars to measure how cosmic expansion has changed over time. These supernovae result from white dwarf stars that explode when they accumulate exactly the same amount of matter from companion stars. The identical trigger mass produces nearly identical explosion brightness. Since astronomers know the true brightness of these explosions, they can calculate precise distances by comparing true brightness with apparent brightness as seen from Earth. Measurements of supernova distances at different cosmic epochs revealed that expansion was decelerating in the past, but has been accelerating for the past 5 billion years. This acceleration provides the primary evidence for dark energy's existence and reveals how this mysterious component has grown to dominate cosmic evolution. The cosmic microwave background radiation carries information about the universe's composition when it was only 380,000 years old. Tiny temperature variations in this ancient light reveal dark matter and dark energy signatures. This radiation represents the oldest light in the universe. It was created when the cosmos first became transparent to electromagnetic radiation after cooling enough for atoms to form. Precise measurements of temperature fluctuations across the sky show how matter was distributed in the early universe. The fluctuation patterns depend sensitively on the relative amounts of ordinary matter, and dark energy. Analysis of these ancient light patterns allows scientists to determine cosmic composition with remarkable precision. The measurements confirm that dark matter comprises about 27%, while dark energy accounts for roughly 68%. The cosmic microwave background provides a baby picture of the universe that preserves evidence of invisible components in exquisite detail. Baryon acoustic oscillations are fossilized sound waves from the early universe. These patterns in galaxy distribution provide independent measurements of dark energy's effects on cosmic expansion. Before atoms formed, sound waves traveled through the hot plasma that filled the early universe. These acoustic oscillations created periodic compression and rarefaction patterns in the cosmic matter distribution. When atoms finally formed and the universe became transparent, the sound waves stopped propagating, but they left behind a characteristic scale imprinted in the matter distribution. Astronomers can detect this acoustic scale by measuring correlations in galaxy positions across cosmic surveys. The scale acts like a standard ruler that reveals how space has expanded over time. Changes in the acoustic scale at different cosmic epochs provide precise measurements of how dark energy has influenced expansion throughout the universe's history. Large-scale galaxy surveys measure redshifts for millions of galaxies to create three-dimensional maps of cosmic structure. These maps reveal how dark matter and dark energy shape structure formation. Galaxy redshifts indicate distances because more distant galaxies have higher redshifts due to cosmic expansion. Measuring redshifts for vast numbers of galaxies allows astronomers to map their three-dimensional positions. These cosmic maps show how galaxies cluster into filaments and walls while leaving vast empty regions called cosmic voids. The clustering patterns depend on the gravitational effects of dark matter. Comparing galaxy clustering at different cosmic distances reveals how structure growth has changed over time. The measurements show that dark energy has suppressed structure formation in recent epochs. Three-dimensional galaxy mapping provides direct evidence of how invisible components govern the evolution of cosmic architecture across billions of light years. Scientists have built ultra-sensitive detectors in deep underground laboratories to catch dark matter particles colliding with ordinary atoms. These experiments search for direct evidence of dark matter's particle nature. Underground locations shield detectors from cosmic rays and other radiation that could create false signals. The deepest laboratories lie more than a mile beneath Earth's surface. The detectors contain extremely pure materials designed to record tiny energy deposits from dark matter particle collisions. Each detector can register impacts with individual atomic nuclei. Despite years of searching with increasingly sensitive equipment, no experiment has definitively detected dark matter particles. The non-detection results place strict limits on how strongly dark matter interacts with ordinary matter. These direct detection experiments represent humanity's best hope for discovering dark matter's fundamental particle nature through laboratory measurements rather than astronomical observations. Indirect detection experiments search for high-energy radiation produced when dark matter particles collide and annihilate each other. These cosmic ray signatures could reveal dark matter's presence throughout the galaxy. When dark matter particles meet their antiparticles, they should annihilate and produce high-energy gamma rays, neutrinos, or other detectable particles. The annihilation rate depends on dark matter density. Space-based gamma-ray telescopes scan for excess radiation from regions with high dark matter concentrations like galaxy centers or small satellite galaxies orbiting the Milky Way. Underground neutrino detectors look for streams of particles produced by dark matter annihilation in the Sun or Earth's center, where dark matter might accumulate gravitationally. So far, indirect searches have found no convincing evidence of dark matter annihilation. The null results constrain theories about dark matter's particle properties and interaction rates. High-energy physics experiments at particle accelerators attempt to create dark matter particles in laboratory collisions. These experiments test whether dark matter consists of particles predicted by theories beyond the standard model. Particle accelerators smash protons together at enormous energies to recreate conditions similar to those just after the Big Bang. These collisions can potentially produce exotic particles, including dark matter candidates. Detectors surrounding collision points look for missing energy that could indicate dark matter particle production. If dark matter particles are created but escape without interacting, they would appear as missing energy. The experiments also search for supersymmetric particles or extra-dimensional particles that some theories propose as dark matter candidates. No clear dark matter signals have emerged from accelerator experiments. These laboratory searches complement astronomical observations by testing specific theoretical models of dark matter's fundamental nature, using the most powerful particle physics tools available to human science. What if dark matter consists of particles that interact incredibly weakly with ordinary atoms? Scientists call these hypothetical particles WMPs, which stands for weakly interacting massive particles. WMPs would have significant mass, but interact with normal matter only through gravity and the weak nuclear force. This combination would make them nearly impossible to detect while still allowing them to clump gravitationally. The weak nuclear force operates only at subatomic distances. WMP particles could pass through your entire body without hitting a single atom. Trillions might flow through Earth every second without leaving any trace. This weak interaction explains why dark matter remains invisible while still affecting cosmic structure formation. WMPs could accumulate into galaxy halos without interfering with star formation or planetary systems. WMP theory predicts that underground detectors should occasionally catch these particles colliding with atomic nuclei, though the detection rate would be extremely low. Could dark matter be made of actions? These hypothetical particles were originally proposed to solve a completely different puzzle in particle physics known as the CP problem. The CP problem involves why certain particle interactions don't violate a fundamental symmetry that physicists expected nature to preserve. Standard physics can't explain this mysterious symmetry preservation. Actions would be incredibly light particles that barely interact with anything. They would be produced in enormous numbers throughout the universe but remain completely undetectable through normal means. If actions exist, they could fill the universe with a sea of invisible matter. Their tiny individual masses would add up to create the missing mass that holds galaxies together. Action detection requires specialized equipment that converts these ghostly particles into detectable photons using strong magnetic fields, making them one of the most challenging dark matter candidates to find. Beyond the 3 known types of neutrinos, could additional sterile neutrinos make up dark matter? These particles would be even more elusive than ordinary neutrinos that already pass through matter like it doesn't exist. Regular neutrinos interact through the weak nuclear force, allowing scientists to detect them occasionally in massive underground experiments. Sterile neutrinos would interact only through gravity. These hypothetical particles would be heavier than known neutrinos, but still much lighter than protons or electrons. They would move more slowly than regular neutrinos, allowing them to clump into cosmic structures. Sterile neutrinos could explain several puzzling observations in neutrino experiments that don't match predictions from the standard model of particle physics. If sterile neutrinos compose dark matter, they would represent the first discovery of particles beyond our current understanding of fundamental physics. Supersymmetry theory predicts that every known particle has a heavier, more massive partner particle. Could these supersymmetric particles make up the missing dark matter throughout the universe? In supersymmetric theories, electrons have partners called selectrons. Quarks have squark partners, and photons have photino partners. These particles would be much heavier than their ordinary counterparts. The lightest supersymmetric particle would be stable and unable to decay into lighter particles. This stability would allow these particles to survive since the Big Bang while remaining invisible. Supersymmetric dark matter would interact weakly with ordinary matter, similar to WMPs but through a more elegant theoretical framework that unifies fundamental forces. Particle accelerators have searched for supersymmetric particles for decades without success, but the theory remains viable if these particles are heavier than current experiments can produce. What if our universe has more than 3 spatial dimensions? Extra-dimensional theories suggest that dark matter might exist in hidden dimensions that we cannot directly perceive. In these theories, ordinary matter remains confined to our familiar 3-dimensional space, while dark matter can access additional spatial dimensions that remain invisible to us. Gravity would be the only force that operates across all dimensions, explaining why dark matter interacts gravitationally but remains electromagnetically invisible. Matter in extra dimensions could influence our 3-dimensional space through gravitational effects while remaining completely undetectable through light or electromagnetic radiation. These theories predict that dark matter particles could disappear from our observable space by moving into higher dimensions, making direct detection nearly impossible with current technology. Quantum mechanics predicts that completely empty space contains vast amounts of energy. Could this vacuum energy be the source of the mysterious dark, energy-accelerating cosmic expansion? According to quantum theory, virtual particle pairs constantly appear and disappear throughout empty space. These quantum fluctuations should contribute energy to the vacuum of space. If vacuum energy has repulsive gravitational effects, it could explain why cosmic expansion accelerates rather than decelerates over time. However, theoretical calculations of vacuum energy density exceed observations by more than 120 orders of magnitude. This represents the worst mismatch between theory and observation in physics history. Either quantum mechanics fails catastrophically on cosmic scales, or vacuum energy gets cancelled by unknown mechanisms that reduce its gravitational effects. Could dark energy be a scalar field similar to the Higgs field that gives particles their mass? These hypothetical energy fields would permeate every region of space with invisible energy. Scalar fields have the same energy density everywhere and don't change with direction. A cosmic scalar field could create the uniform repulsive force needed to accelerate expansion. Unlike the Higgs field, which has a constant value, dark energy fields might slowly evolve over cosmic time. This evolution could explain why dark energy dominance began relatively recently. Different scalar field models predict different evolutionary patterns for cosmic acceleration. Some fields would create accelerating expansion that continues forever, while others might reverse direction. Future observations of cosmic expansion history will test whether dark energy behaves like a constant cosmological term or evolves like a dynamic scalar field. What if dark matter and dark energy don't exist at all? Modified gravity theories propose that Einstein's equations need correction at cosmic scales rather than requiring invisible components. These theories suggest that gravity behaves differently over galactic distances than it does within the solar system. The modifications could explain galaxy rotation curves without invoking dark matter. Modified gravity could also account for cosmic acceleration without dark energy by changing how space-time responds to matter and energy at cosmic scales. The most successful modified gravity theory is called MOND, which stands for Modified Newtonian Dynamics. It correctly predicts many galaxy properties without requiring dark matter. However, modified gravity theories struggle to explain observations of galaxy clusters and the cosmic microwave background radiation that seem to require actual dark matter particles. Could dark energy change its strength over cosmic time? Quintessence models propose that dark energy behaves like a slowly rolling ball that gradually changes its properties. Unlike the cosmological constant, which remains perfectly constant forever, quintessence energy density could increase or decrease as the universe evolves. These models use scalar fields that change value over billions of years. As the field evolves, its energy density and pressure properties shift, altering cosmic expansion rates. Some quintessence models predict that dark energy was weaker in the past and has grown stronger over time. Others suggest dark energy might weaken in the future, or even reverse direction. Variable dark energy could explain why the transition from decelerated to accelerated expansion occurred relatively recently in cosmic history rather than earlier or later. Could dark energy result from interactions between our universe and other parallel universes in a multiverse? Some theories suggest that multiple universes exist simultaneously in higher dimensional space. If our universe sits next to other universes in extra dimensions, gravitational or quantum interactions between them might create repulsive forces within our space. Energy could leak between parallel universes through quantum tunneling effects that operate across higher dimensional boundaries. This leaked energy might manifest as dark energy in our cosmos. Multiverse theories predict that dark energy strength should vary depending on the number and proximity of neighboring universes, creating testable consequences for cosmic evolution. These models remain highly speculative because parallel universes cannot be observed directly, making multiverse explanations for dark energy nearly impossible to verify experimentally. What if dark matter and dark energy are illusions created by systematic errors in astronomical observations? Could humanity be misinterpreting cosmic data due to unknown biases or measurement mistakes? Astronomical observations rely on complex chains of assumptions about stellar physics, cosmic distances, and light propagation across billions of years. Errors in any step could create false evidence for invisible components. Dust extinction, gravitational lensing, or unknown astrophysical processes might systematically dim distant supernovae, creating the false appearance of cosmic acceleration. Similarly, unrecognized magnetic fields or plasma effects might alter galaxy rotation measurements, creating the illusion that invisible matter dominates galaxy masses. While most scientists consider systematic errors unlikely given the diversity of supporting evidence, the possibility remains that fundamental assumptions about cosmic observations could be wrong. Modern cosmology now operates under a completely new standard model. Scientists call it lambda CDM, which represents the current best description of cosmic composition and evolution. The lambda refers to dark energy, represented by Einstein's cosmological constant. CDM stands for cold dark matter, the invisible particles that dominate galaxy formation. This model specifies exact percentages for each cosmic component. Dark energy comprises 68% of the universe. Dark matter accounts for 27%. Ordinary matter makes up just 5% of everything that exists. Lambda CDM successfully explains observations ranging from galaxy formation to cosmic microwave background patterns. No alternative theory matches this model's predictive power across multiple observation types. The model's success has transformed cosmology from speculative philosophy into precision science with testable predictions and quantitative accuracy. Galaxy formation becomes impossible without dark matter's gravitational scaffolding. Computer simulations demonstrate that visible matter alone cannot create the cosmic structures we observe today. In simulations without dark matter, ordinary matter remains dispersed as thin gas throughout cosmic space. Gravity from visible matter proves too weak to overcome cosmic expansion and collect into dense clumps. Dark matter provides the initial gravitational seed points where normal matter can begin accumulating. The invisible matter forms halos first, then captures ordinary matter within their gravitational wells. This process explains why galaxies exist at specific locations rather than being randomly scattered throughout space. Dark matter determined where galaxies could form billions of years ago. Structure formation theory now completely depends on dark matter's invisible architecture to explain how cosmic complexity emerged from initial simplicity. The universe has experienced a fundamental transition in its controlling forces. For most of cosmic history, matter dominated through gravitational effects. Recently, dark energy took control. The transition occurred when the universe was about 7 billion years old. Before this point, matter density exceeded dark energy density and cosmic expansion was decelerating gradually. After the transition, dark energy density surpassed matter density and cosmic acceleration began. This marked the most significant change in cosmic evolution since the Big Bang itself. The shift happened because matter density decreases as space expands while dark energy density remains constant. Eventually, constant energy overtook declining matter density. This cosmic regime change determines everything about the universe's future evolution and ultimate fate across trillions of years ahead. Dark matter and dark energy discoveries have shattered the standard model of particle physics. Our most successful theory describes only 5% of cosmic reality while failing completely for the remaining 95%. The standard model perfectly explains atomic structure, chemical reactions, and electromagnetic phenomena. Every particle accelerator experiment confirms its predictions with extraordinary precision. Yet this triumphant theory remains utterly silent about dark matter particles or dark energy's nature. It provides no candidates for dark matter and no explanation for cosmic acceleration. Physicists must now develop entirely new theoretical frameworks that extend beyond current knowledge. The discoveries demand revolutionary advances in fundamental physics. These theoretical challenges represent the greatest opportunity for scientific breakthrough since quantum mechanics and relativity transformed physics a century ago. Humanity's cosmic status has undergone a profound philosophical downgrade. We're not just small in space and time. We're made of cosmic minority matter in a universe dominated by invisible forces. Previous scientific revolutions moved Earth from the cosmic center, but humans remained composed of normal matter in a comprehensible universe governed by familiar physics. The dark universe revolution strikes deeper. Even the atoms comprising human bodies represent cosmic afterthoughts in a reality governed by completely unknown components. This discovery challenges fundamental assumptions about the nature of reality itself. If 95% of existence operates beyond human perception, what else might we be missing about the universe's structure? The philosophical implications force humanity to acknowledge our profound ignorance about the cosmos we inhabit and our marginal role in its evolution. The search for dark matter has accelerated technological development across multiple scientific fields. Ultra-sensitive detection equipment developed for particle physics now benefits medical imaging, national security, and industrial applications. Cryogenic cooling systems designed to eliminate thermal noise in dark matter detectors have improved medical MRI machines and quantum computers. Crystal purification techniques enable better semiconductor manufacturing. Underground laboratory construction has advanced geological engineering and deep excavation methods. Radiation shielding technologies protect both experiments and space missions from cosmic radiation. Computer algorithms created to analyze massive datasets from cosmic surveys now power artificial intelligence applications and financial modeling systems. The technological spillover from dark matter research demonstrates how fundamental science drives practical innovation across unrelated industries and applications. Dark energy now determines the universe's ultimate destiny. If current trends continue, the cosmos faces either heat death through maximum expansion or catastrophic destruction in a Big Rip scenario. Heat death would result from endless expansion that separates all matter beyond interaction distances. Stars would burn out, galaxies would dissolve, and even black holes would eventually evaporate through Hawking radiation. The Big Rip scenario occurs if dark energy strengthens over time. Eventually, dark energy would overcome all other forces and tear apart every structure from galaxy clusters down to individual atoms. Both possibilities result in a universe where no complex structures can exist. Life becomes impossible across all cosmic scales, regardless of technological advancement. Dark energy's dominance has shifted cosmic evolution from a story of increasing complexity toward inevitable simplification and ultimate emptiness. Dark matter and dark energy discoveries transformed cosmology into a precision science. Astronomers can now measure cosmic parameters with accuracy that rivals laboratory physics experiments. Modern cosmic surveys measure distances, expansion rates, and structure growth with uncertainties below 1%. This precision enables detailed tests of theoretical models and discovery of subtle evolutionary effects. Space-based telescopes eliminate atmospheric interference and achieve unprecedented measurement accuracy. Ground-based arrays coordinate observations across multiple continents for enhanced resolution. Statistical analysis of millions of galaxies provides cosmic parameter measurements that would have been impossible with smaller datasets. Big data techniques enable extraction of subtle signals from cosmic noise. This observational revolution has elevated cosmology from descriptive astronomy to quantitative physics with predictive power and experimental testability. The dark universe discoveries revealed that modern physics fails catastrophically when applied to cosmic scales. Our most fundamental theories cannot explain the majority of cosmic reality. General relativity requires modification with ad hoc additions like dark matter and dark energy to match observations. These additions represent admissions of theoretical ignorance rather than genuine understanding. Quantum mechanics predicts vacuum energy densities that exceed dark energy observations by more than 100 orders of magnitude. This represents the worst theoretical failure in physics history. Particle physics offers no viable candidates for dark matter despite decades of theoretical development and experimental searches across multiple energy scales. These failures demand revolutionary advances in theoretical physics that may require abandoning current paradigms and developing entirely new conceptual frameworks. The invisible universe discoveries have imposed profound intellectual humility on humanity. Our species has learned that 95% of cosmic reality operates completely beyond our current comprehension. For centuries, humans believed that improving telescopes and developing better theories would eventually reveal all cosmic secrets. The visible universe seemed to contain the essential information needed for complete understanding. Dark matter and dark energy shattered this confidence permanently. No amount of optical improvement can make invisible matter visible. No straightforward theoretical extension explains dark energy's nature. These discoveries force recognition that human sensory capabilities and intellectual frameworks may be fundamentally inadequate for understanding cosmic reality. Our cosmic ignorance appears deeper than previously imagined. This humbling realization represents a crucial step toward mature scientific wisdom that acknowledges the vast scope of unknown phenomena awaiting future discovery.